Okay, hi, it's Miss Skelton here. Even though I'm not in class with you today, we're still going to go over transformations of exponential functions. We're going to use a couple examples on this worksheet to get you to where you need to be. Thankfully, you have a lot of prior knowledge about transformations in general, and we're just going to take those transformations and extend it to exponential functions. So the hardest part is just knowing what actual parent function we're starting with. They're all going to be exponential. However, you're going to have to look at the base to tell you which starting points to use. For our actual shifting of the graph, you know how we usually talk about A, B, C, and D, where those values are? And in our equations today, we're always going to have our base to some power, but then we're going to be looking for any vertical changes in the front, vertical stretches and compressions. We're always going to factor out, I'm going to use capital B here, we're always going to factor out any necessary horizontal compressions or stretches or reflections. We're going to be doing the opposite of the sign we see with X if we have any shifting left or right. And then at the very end of the equation, we're still going to look for shifting up and down. And if you want to make yourself a note as we do this, if we were in class, I'd have you figure it out yourself, but this is going to shift our horizontal asymptote up and down. Okay, so let's go ahead and look at the first one. Oh, another thing about the base, remember the base for growth is going to be greater than 1. If we have a decay function, remember that base is between 0 and 1. Notice the base is never negative. So when I look at number 1, the base function here, 2 is being raised to that power, not the negative. So the parent function we're going to start with is 2 to the x, and then we'll apply its transformations in just a second. Okay, so for every parent function, we're going to use the same 3 x's, -1, 0, 1. Our asymptote always starts off as y equals 0 unless we shift it up or down. And then to get these values, you're going to raise 2 to the x power. So when we do 2 to the negative first power, we said that flips that value. It gives us the reciprocal. 2 to the 0 power is 1, and 2 to the first power is 2. And so we're going to start to see we always have the reciprocal of the base, 1, and then the base itself, or our 3y values to start with. So since this is our first one, I'm going to sketch it in, I guess in red, -1, 1/2, 0, 1, 1, 2. Okay, let me use here's my horizontal asymptote. Okay, so this is just y equals 2 to the x, not the transformed one that we're supposed to be graphing. Okay, so now for our transformed, let's look and see. I have a negative in front of my equation, and so that's going to be a vertical reflection, reflect over the x-axis. I also have a shift, but since it is with the exponent x minus 1, I'm going to be shifting the graph to the right by 1. So let's see what that's going to change. To move all my x's right 1, I'm going to have to add 1 to them. To reflect all of my values, remember this is a vertical reflection, so it affects your y's, I just have to change their sign. So I'm going to take all these original y's and change their sign. Let's make these changes. So adding 1 to your x's, go ahead and change your sign on your y's, so -1/2, -1, -2. And then since the asymptote is a y, we're going to plug it into the y value. So change its sign. Well, it's still going to stay y equals 0 because we did not shift the graph up or down. So let's plot these 3 new points and make sure that it shifted right 1 and did reflect. Let me go change colors. 0, negative half, 1, negative 1, and 2, negative 2. Looking pretty good. Yes, so you can tell a slight shift to the right, and it definitely reflected. Its domain, we are not capable of changing. Okay, it's going to always be negative infinity to infinity because we're not restricting the x's in any way. Our range, now that we reflected it, it looks like our y's go from negative infinity up to 0. Make sure you don't include the 0 since it's the asymptote and the graph does not reach it. Intercepts, I only have a y-intercept. I can see it in the table. Remember, I can always plug in 0 for x to make sure it's right, but it ends up being negative 1/2. Interval of increase or decrease. So we're describing the transformed graph as it's still technically a growth graph, but when it gets flipped, as I trace it from left to right, it's now a decreasing graph, and it's decreasing always. So it's going to decrease from negative infinity to positive infinity. And it only changed to decreasing because of the reflection. Okay, end behavior, your favorite. So let's see, as x approaches negative infinity on the left side, I can see the y's are approaching the asymptote, getting closer and closer to 0. As x approaches positive infinity, the y's are approaching, on the right side, the graph is pointing down, so negative infinity. Okay, exciting. Okay, we are going to go ahead and do another one. We need to pick one that is decay. So let's see. Just looking, I didn't realize that was cut off. Now I did, so I'll leave it there for just a second. As I look down at number 2 and get a head start, we're not actually going to do it because I can see it's 4 to the x minus 2. So this is a growth function with a base of 4. So I'm going to let you try that one and check with the key. I can see on 3 and 4 that they both have a base that's a fraction. I see a half here. I see a fourth here. I know that this one has some not nice fractions, so let's go ahead and do 4, because I think it's the more painful one. Okay, so I have a base of a fourth, so my parent function is 1/4 to the x power, and it's going to help me get my table set up initially. So I'm going to use the same 3 x's every time, and when I make the exponent -1, I get the reciprocal, so I'm going to get 4. Raise the 1/4 to the 0 power, I get 1. Raise it to the first power, I get the same fraction back. The original asymptote is always y equals 0. Okay, now let's talk transformations. So, I see I have 2x plus 6 in my exponent, so we're going to have to factor out that 2, that b value, and it gives me an x plus 3. Okay, so as I look at my transformations, the exponent is everything horizontal. So this 2, I know everything is opposite, so we have a horizontal compression of a half. I know the x plus 3 tells me I'm actually shifting left 3, and a minus 5 at the end means that we're moving the whole graph down 5. Because there's not a value in front of the base multiplying, there is not a vertical stretch or compression or reflection on this one. Okay, so let's go ahead and talk about how do these changes affect my x's and y's. If we want to compress the x's, multiply them by a half, and then if I need to shift them left 3, subtract 3. If I need to just move my y's down 5, then y minus 5. Okay, so maybe the numbers won't be too bad. Okay, so as I plug in the original x, negative 1 times a half, that'd be negative half minus 3, so negative 3 and a half, or 3.5, or 7 halves, any way you'd like to represent it is okay with me. Plug in your original x of 0. A half times 0 is 0, and minus 3 is negative 3. Plug in your 1. 1 times a half is a half, minus 3 is negative 2 and a half, or 2.5, or 5 halves. Okay, let's subtract 5 from every y, so I'm going to get negative 1 and negative 4, and then 1/4 minus 5. You can do it however you'd like. 1/4, if you want to change it all into fourths, you could, right? It would be 1/4, but you'd have to change the 5 into fourths, minus 20/4. So it would be negative 19/4, or that means it goes in 4 times with 3/4 left over. So negative 4 3/4 would be fine there as well. And then plug in 0 as my y value, and it shows me that the asymptote shifts to negative 5. And I'm going to go ahead and sketch that first. Okay, this was a decay function that did not reflect, so I should still see a decaying function. Let's see if we did it right. So negative 3 and a half. I'm just going to graph the new one, not the parent function. 1, 2, 3 and a half, and down 1. Okay, there's my first ordered pair. Negative 3 and negative 1, 2, 3, 4. And then negative 2 and a half. And really close to that asymptote. There we go. So like we said before, our domain is going to stay negative infinity to infinity. Our range, I can see this graph is above its horizontal asymptote. So its y's are above negative 5 and continue to infinity. Its intercept is not in the table. Interesting. So let's go do this. And y'all, most of the time I'm not going to ask you to find the intercept if it takes a lot of work. But we could plug in a 0 for x. And we're going to get what? Let's see. 1/4 to the 2 times 0 plus 6 power. To the 6th power minus 5. Okay, I would let you use a calculator if you were going to do something like this. Yeah. I can tell it's very, very close to negative 5. And I did type it in the calculator earlier. It was negative 4.99. But again, don't expect to be asked about intercepts. For the most part, it's just going to be the table, identify the transformations. As I look from left to right, this graph is decreasing. And its end behavior as x approaches negative infinity. So as I look at the left side of the graph, those y values are approaching positive infinity, and I can see that function pointing upwards. As x approaches positive infinity on the right side, I can see the function getting closer and closer to its horizontal asymptote, which is -5. Okay, so you have 3 more transformation tables that you're going to do on your own or in your group and see if you're on the same page. You can check with the key that I posted on Canvas. But we're going to do 2 more problems on the back that are a little bit different. So turn to the back. We're going to do number 6 and something at the end. So let's do 6 first. Okay, 6 is tricky because it asks us to describe the transformations performed on f of x that create g of x. And some of these points are labeled for us. So it says -1.5. That gives me a good idea of the function f of x. This looks like the point 0, 1. And then I see the point 1, 2. And we want to compare the x's and the y's to see these transformations. Okay, so let's look at our x's. -1 became -0.5. 0 stayed with this point here that had a 0, 2. Okay, so 0 stayed 0. Compare the x on the third point. 1 became 1/2. So if you need a label, this is the original. G of x is the new one. So all the x's, it looks like they multiplied by 1/2, and that was the only change I see. So I'm going to label that a horizontal compression by 1/2, and then we'll talk about how that affects the equation in a second. When I compare all the y's, 0.5 became 1.5, 1 became 2, 2 became 3. It looks like it just shifted up 1. So when it says write an equation for g of x in terms of f, and we can go over this more next class, but this is where I want to include the f in my equation. I'm not going to make it look exponential. I'm just going to show these transformations, my horizontal compression. I have to show the reciprocal here. The x's got horizontally compressed by 1/2, so I put 2x. And if I want to shift the graph up 1, plus 1. Okay, when you look at the next ones, again, they're more complicated than what you would see on a quiz or test, or maybe I'd put something multiple choice on there, but give them a shot, see if they make sense, star anything we need to talk about next time, and let's go pick one of these from the end over here. It lists the transformations in function notation, so let's see, maybe I will pick I don't know, maybe 13 down here. So it says, describe the transformations performed on m of x to create t of x. Okay, and then we want to actually write the exponential equation, not just in function notation. Okay, so as I look at this, I can see there were changes made to the x's, and I do have to separate that 3 from the rest of the expression. So I'm going to divide a 3 out. So m of, or t of x equals m of, and then I separated out the 3 and x minus a third. So it looks like I have a horizontal compression. The 3 would become the scale factor, 1/3. And then I'm also shifting the graph right, but only by a third once I divide that 3 out. So if I wanted to actually change it back to exponential form, I would use the base that m had, so it would still be the base of 4. And then to show these changes, that's all part of the exponent. you could leave it factored like this, or you could technically multiply it back, but now I changed it from function notation to equation. Let's do 12 right above it, and then that'll be it. Okay, so 12 had a base of e. Oh, I've written way too much. And then I can see m of x here, where the 1/2 is clearly in front, and this plus 4 is not with x at all. So it looks like this is going to be a vertical compression of 1/2. Plus 4 at the end is going to be shifting my graph up 4. And so when we go to write that equation, it was e to the x, but if it gets compressed by 1/2, we're going to put a 1/2 in front. If we want to shift it up 4, we're going to clearly put a plus 4 at the end that is not part of that exponent. And then that's it. So that's kind of different ways I could ask you about these. Next class, be prepared to ask questions. We do have a paper quiz, but it'll be like transformation tables, like the first examples. We'll have time to practice first. And you're also today going to do a Mastery Connect I posted on Canvas, but you'll be able to work in your group and use each other and your notes as you answer those questions. So I will be back tomorrow and available for tutorials if you need me.